All right, folks, dimensional analysis. You are going to use this all year. It's not going to go away. Please, please, please learn this now. Learn this now while the problems are easy. That way, when the problems get hard, you already know the process and the process makes sense to you. Sometimes students do some of these easier problems. It's like, I don't need the dimensional analysis here, so I'm not going to do it. And then they don't know how to do it when we do the harder problems where there's no other way to think through the problem. So please learn it now. What is dimensional analysis? Dimensional analysis is a problem-solving method that uses the units, the dimensions of the measurements involved in the calculation. It uses the idea that any number multiplied or divided by 1 does not change its value. It also uses the idea that units can be multiplied and divided, just like numbers. And it uses conversion factors to change from one unit to another. So, what's a conversion factor? A conversion factor is a definition. It's a definition that you write as a fraction that is equal to 1. We use conversion factors to get rid of old units by dividing them away, and to introduce new units needed for the final answer by multiplying them in. There are always two ways to write a conversion factor, but only one way is going to be correct for a particular problem. So part of the trick in answering any dimensional analysis question is making sure you've got the conversion factor the right way around. So far I've been giving you vague definitions. It sometimes is more helpful to see an example. So here's one example. 1 foot is defined as being 12 inches. That's a definition. 1 foot equals 12 inches. So there are two conversion factors I could write with this. I could write the feet on top and the inches down below, or I could write the inches on top and the feet down below. These are both fractions that are equal to 1. I know that 1 over 12 and 12 over 1 don't look like they're equal to 1, but because of the units, they are equal to 1. 1 foot is the same as 12 inches. 12 inches is the same as 1 foot. Another example would be 1 minute equals 60 seconds. There are two ways to write this conversion factor, either with the 1 minute on top and the 60 seconds down below. Those two quantities are equal. Or with 60 seconds up top and 1 minute down below. Those two quantities are equal. Remember, the bigger unit gets the smaller number. So minutes are bigger than seconds. So the smaller number goes with the bigger unit. And similarly, the big number goes with the small unit. Sometimes students make mistakes and they'll say 1 second is 60 minutes. You need to check to make sure you're writing it the correct way. Okay. There are always two ways to write a conversion factor, but only one way is correct for a given problem. So I'm going to show you a dimensional analysis problem and we'll see which way we need to have our conversion factor. So if I want to know how many feet are in 32 inches, there are two different conversion factors I could use. 12 inches for 1 foot or 1 foot for 12 inches. How could I do this problem? Let's see what happens when I use the first conversion factor. I start with 32 inches and I try to multiply by my conversion factor. I have 12 inches on top and 1 foot down below. So let's look what happens when we do that. I multiply my numbers together. 32 times 12 divided by 1 is 384. But let's look at what happens to our units. Inches times inches divided by feet. So inches times inches is inches squared, and I still have to divide by feet. Okay, those are kind of weird units. I don't really know what that even means, inches squared divided by feet. So when I round off to two significant figures, because this is a multiplication problem, so I need to round off to the appropriate number, 2 sig figs, this doesn't make sense. It's mathematically correct, but my units are a big mess and they don't mean anything. I just wanted to have feet as my answer, not this big mess. Let's see what happens when we try the other conversion factor. When I try the other conversion factor, I have 32 inches times 1 foot divided by 12 inches. Notice that my inches cancel out. I have inches up top in the numerator and inches down below in the denominator. And because of that, they cancel out. I'm dividing it away. So my inches actually disappear. And the only units I have left are these feet. So when I do the multiplication, 32 times 1 divided by 12, I have 32 divided by 12, which is 2.666667, however many decimal places your calculator goes to. When I round off to 2 sig figs, that's 2.7 feet. And notice those units make a lot more sense. Those units were the units I wanted. Okay? So when we look at dimensional analysis, we're going to look at making sure we've got the conversion factor in the right orientation that lets the old units cancel out. We want the old units to cancel out. And we will look at these step by step. Right now, this is an overview of the dimensional analysis method. Okay, so both of these statements are mathematically true statements, but only one of these statements actually answers our question. How many feet are there in 32 inches? Option B answers that question. Okay, one more thing here in the overview before I give you the step-by-step process. Again, we choose the one conversion factor that divides away the old units by putting them in the denominator. So I started with inches and I want to get rid of inches. So I want to make sure my conversion factor has inches in the denominator. I also want to make sure that my conversion factor brings in the new units in the numerator. In this case, my new units are feet because that's what I want my final answer to be in. There's another way to write dimensional analysis that I prefer, and I call it the train tracks method. It's the same exact problem, just written in a slightly different method because it makes things more tidy on a piece of paper. I start with 32 inches, just like I did before. I have my conversion factor. I have something up top and something down below, 1 foot on top, 12 inches down below. And I still multiply to get my answer. And I end up with the same answer. But just this kind of cross method here, it's just tidy. You multiply everything that's up top, you divide by everything that's down below, and some students find it easier because you keep things more organized this way. Okay, that's the overview of dimensional analysis. Let's break it down into 5 steps so that you can copy the procedure and figure out problems on your own. So the very first step in dimensional analysis problems is to write the known, the thing that you're given in the problem, and identify the unknown, the thing that you want to know, what the question's actually asking for. The second step is to draw the dimensional lines, those train tracks or the multiplication symbols. The third step is to insert the correct conversion factor. Then remember that old units go into the denominator, new units go into the numerator. And then it's just a double extra check. Make sure that your units cancel correctly. Make sure that you've put the conversion factor in the right direction. And then step 5 is to do the math. When you're done doing the math, check to make sure that you've remembered your units and check to remember that you have the correct number of significant figures. It's important when you're doing the math that you follow the order of operations. You're always going to multiply values in the numerator and you're always going to divide by values in the denominator. So let's look at an example where we do each of those 5 steps one by one. So how many quarts is 9.3 cups? First, I have to write my known and identify my unknown. What is the known? I know that I have 9.3 cups, so I'm going to write that down first. What don't I know? What am I trying to find out? I don't know how many quarts I have. That's my unknown. So I'm going to write quarts at the very end of my problem because I don't want to forget to write quarts at the end, and I also want to just remember what I'm aiming for. So that's it. We've done step 1. Let's look at step 2. We're going to draw the dimensional lines. I'm only going to need one conversion factor to move from cups to quarts. So this is enough in terms of my dimensional lines. Next, I need to insert the correct conversion factor. I need to know how many cups are in a quart. This is not something I expect you to have memorized for my class. It's something that you would need to look up. But there are 4 cups in 1 quart. So I have 2 possible conversion factors that I could use. I could have 4 cups on top, 1 quart underneath, or I could have 1 quart on top, 4 cups underneath. Which one should I use? Well, remember, I want the old units to be in the denominator. My old units are cups. I want the new units to be in the new numerator. My new units are quarts. So I want cups on the bottom, quarts on the top. Therefore, the circled conversion factor is the one I want to use. I put cups down below, quarts up top, and then I make sure I write the correct numbers next to those units. 4 cups is the same as 1 quart. Step 4 is to check to make sure that the units cancel correctly. We're just double checking to make sure we had the right conversion factor here. Cups divides away from cups, and quarts are left, which is good because I have quarts for my final answer. So yes, my units cancel correctly. Step 5 is to do the math. Follow the order of operations, multiply by values in the numerator, and divide by values in the denominator. Also, when you do the math, remember your units and your significant figures. So I'm going to have 9.3 times 1 in the numerator and 4 in the denominator. So that is the same as 9.3 divided by 4. And that's 2.325 quarts, but that has too many significant figures. I need to look at how many significant figures I had in my original value. Since I had 2 sig figs here, I need to have 2 sig figs in my final answer. So I'm going to round off my value at this position. Because the 2 is less than 5, I don't have to do anything to this 3, and I have 2.3 quarts. Now, students are sometimes curious. They think, hey, wait a second, this is 1 significant figure, and this is 1 significant figure. So why don't I have 1 significant figure in my answer? Remember, a definition has infinite sig figs. So this is a definition. 1 quart equals 4 cups. We could say 1.000000000 quarts and go on forever is the same as 4.000000000 going on forever cups. These have infinite sig figs, so these conversion factors do not impact how many sig figs I can report in my final answer. So the general rule is however many sig figs you start with in your initial value is the number of sig figs you can have in your final answer. Okay? So we did that problem very slowly, step by step. We saw how each step lined up with the 5 steps that I've given you. So let's look at another example. 1 pizza has 12 slices. How many slices are in 7 pizzas? Step 1, figure out your known, figure out your unknown. What's our known? We know that we have 7 pizzas. We want to know how many slices we have. So I write down 7 pizzas at the beginning and slices at the end. Step 2. Oh, before I move on to step 2, sometimes students get confused here. They think, I know that one pizza has 12 slices. This is my conversion factor relationship. You wouldn't have known if I hadn't told you how many slices were in this particular kind of pizza. So this is going to be my conversion factor relationship that I'm going to use in step 3. Okay. Step 2 is to draw the dimensional lines. Step 3 is to add in the conversion factor. Remember, I have 2 choices for my conversion factor. Should I have pizza on top and slices down below, or slices on top and pizzas down below? Remember, I want the known units to be in the denominator so that they cancel out and divide away. So I want pizza to be on the bottom, slices to be on the top, and then I need to make sure I write the correct number next to each value. Step 4 is to check that I did the conversion factor correctly, that my units do cancel out. Get rid of the pizzas. I'm left with slices, which is good because that's what I want to have in my final answer. And step 5 is to do the math. I multiply by everything up top, divide by everything down below, and I end up with 84 divided by 1, which is, in fact, 84. You may be asking yourself, wait a second, we started with 7 pizzas, which has just 1 sig fig. Why don't I write my answer to just 1 sig fig? This comes back to the idea that number of pizzas is a counted quantity. If I have exactly 7 pizzas, if I haven't eaten half of one of the pizzas yet, it's a counted quantity and it has infinite sig figs. So we could say that we have 7.000000000 going on forever, significant digits in this number, because it is a counted quantity. Because of that, it's okay to write 2 sig figs in our answer here. Again, this is also a counted quantity, so this is actually also has infinite significant figures. These counted quantities don't limit the number of sig figs that you can have in your answer. Okay. You don't have to use the train tracks method. You can use fractions and multiplication signs. So that just looks like this. It's 7 times 12 slices, 7 pizzas times 12 slices divided by 1 pizza. The pizza still cancels out, and you still end up with 84 slices as your answer. Okay, let's do another example. How many days are there in 17.0 years? Our known is 17.0 years, and what we want to find out, our unknown, is how many days we have. So I'm going to write days at the end, 17.0 years at the beginning. Step 2, I'm going to insert the dimensional analysis lines. Step 3, I need a conversion factor. Hopefully you know that there are 365 days in 1 year. And so we have 2 choices for the conversion factor. We can have the days on top and the year down below, or the year on top and the days down below. I want to have the years down below so that the years cancel out when I get to step 4. Check to make sure that my old units divide away and I'm just left with my new units of days for my final answer. And then I do the multiplication and division. 17 times 365 divided by 1. I end up with 6205 divided by 1. So 6,205. Now, my initial value had just 3 significant figures. Therefore, my answer should just have 3 significant figures. 6,210 days about in 17 years. Okay. Again, you can do the same example using multiplication signs. I prefer the train track method, but just to show you how that looks, the years still cancel out with years, and you still should end up with 6,210 days. Let's do another one. There are 2.54 centimeters in 1 inch. How many inches are in 17.3 centimeters? 17.3 centimeters is our known. Our unknown is how many inches we have. We're also given a conversion factor in this problem. So don't get that conversion factor confused with what the known and unknown is. So doing this problem, our known is 17.3 centimeters. Step 2 is we have to draw the dimensional lines. Oh, we're trying to work our way to inches, so I'll put that at the end here. We draw our dimensional lines, and now I have to insert my conversion factor. I could have 2.5 centimeters with 1 inch, or I could have 1 inch with 2.54 centimeters. Which one do I use here? I use the one that'll put centimeters in the bottom to cancel out the centimeters here. 2.54 centimeters is the same as 1 inch. So when I do the math, I end up with 17, I'm sorry, I skipped step 4. I shouldn't do the math yet. Step 4 is to check to make sure my units cancel. They do. And now step 5 is to do 17.3 times 1 is still just 17.3, and I divide by 2.54. And I get, oh, my calculator gives me a big long answer, 7.8110, and it goes on a bit. My start value has just 3 significant figures, 1, 2, 3 significant figures, so I trim here. And because of this, 6.81 inches is my final answer. Okay. And here you're just checking your answer. So 6.81 inches is your final answer. One more practice problem for these one-step dimensional analysis problems. Determine the number of eggs in exactly 23 dozen eggs. My known is the 23 dozen. My unknown is the number of eggs. So step 1, I'm going to write down the 23 dozen, and I know I'm trying to get to eggs at the end. And I'm going to go ahead and insert the dimensional line, so I'm ready to write down my conversion factor. With these conversion factors, I expect you to know that there are 12 objects in a dozen. So I can either use 12 eggs are in 1 dozen, or 1 dozen is the same as 12 eggs. Which one should I use? I need to use the one that has the dozen down below. So 1 dozen is the same as 12 eggs. Step 4 is to check to make sure that my units cancel, and they do. Step 5 is to do the math. So I end up with 23 times 12 divided by 1. And 23 times 12 is 276. So 276 eggs is my answer. Now, like before, you may think, hey, 23, I only had 2 sig figs here at the start. Shouldn't I just have 2 sig figs in my answer? 23 is a counted value. Counted values have infinite sig figs. So if you count 23 dozen, if you have exactly 23 dozen eggs, then that has infinite sig figs. Therefore, that does not limit my sig figs here, just because it is a counted value. So again, checking your work, if you did the multiplication fraction method, the dozens still should cancel out, and you still end up with 276 eggs as your answer. So these are a few examples of single-step dimensional analysis problems. We do need to know how to do multi-step dimensional analysis problems also. So that will be in a separate video. Hope this helps.